Well, we get a lot of these triangle questions. So whenever you're given one of the ratios, sine, cos, tan, whichever one it is, it should immediately make you think of a triangle question. And the triangle, the first thing you have to do is draw where that triangle is going to be in which quadrant. So it tells us that cos of theta is 3/8 and it's not in quadrant 1. Which quadrant is it going to be in? It's going to be in the fourth one. How do we know it's in the fourth one? Because cos is positive, and you can label your reference angle there. And once you found out which quadrant your angle's in, you can draw that triangle back to the nearest x-axis. Again, that triangle always has to go back to the nearest x-axis so that you can label your reference angle. And then based on this reference angle, if I was going to label the 3 and the 8, cos is adjacent, so the 3 would go here, and 8 is the hypotenuse, would go there. You are going to get really good at mental math with a squared plus b squared equals c squared. Give it a try. Put up the answer in a couple seconds. All right. How'd you do? Square root of 55. That's not the hypotenuse, so you can't add them. You'd have to go 64 minus 9, get the 55, square root of 55. So we want to find sine of theta. This would be a non-calculator question, sine of theta, opposite over hypotenuse. And because it's in quadrant 4, what do we know about sine in quadrant 4? It's negative. That's going to be the thing you're going to miss. So we always got to check what quadrant is it in. Think about your cast rule. Since it's in quadrant 4, only cosine is positive in quadrant 4. So sine would be negative. What about tan? Oops, tan. Hey, that's a good mistake I just made. I forgot the theta. Do not forget the theta. It'll also be negative because tan is negative in quadrant 4. Yes. No. When you have a fraction, right, if I have root 55 over 3, you could have the negative in front like that. That would make the whole fraction negative. That is equal to having the negative on the top, which is equal to having the negative on the bottom. No, not for marking. All three of those are considered equivalent, and it's fine either way. Generally, this is probably seen the least. Somehow having the negative in the denominator, people don't like that as much. So you either see it in front of the whole thing or on the top. Question 2. Is that point on the unit circle? Well, if we look at those coordinates, did that appear when we made our unit circles? Did you ever see those numbers? No. But when we made our unit circle, we only did certain points. There's a whole bunch of other points that we didn't label. So how do we find out for sure if this point is on there or not? Well, one way that you could look at it is if it's on the unit circle, we had the formula for our unit circle was this, which led to the big idea. Do you remember this big idea? That sine squared plus cos squared equals 1. So if that point is on the unit circle, then this has to be true. So we can check what happens when we take root 3 over 3 and square it and add it to root 6 over 3 and square it. What do we get? Well, this becomes 3 over 9 plus 6 over 9. And 3 over 9 plus 6 over 9 equals 9 over 9. And 9 over 9 is equal to 1. So yes, It is on the unit circle. If that number did not come out to equal 1, then it would not be on the unit circle. So that is how we can tell if a point is on the circle or not. Sine squared plus cos squared would have to equal 1. And so you could do one value squared plus the other one squared and check. If it's equal to 1, then that point is on the unit circle. We've got another point, negative 12, 13, comma y is a point on the unit circle in quadrant 3. Find y. So again, another triangle question. We know it's in quadrant 3, so we can draw it in quadrant 3 with our reference angle. And if we know the x-coordinate is negative 12 over 13, what does that tell us? That tells us that cos is negative 12 over 13. So I know that cos is adjacent over hypotenuse. If I was labeling lengths of this triangle, this would be 12 and this would be 13. It's not bad if you add the negative there, but you can just label them with positive values if you like. Oh, I have to get off topic with this one again too. Okay, sorry. But we'll finish the question first. A squared plus b squared equals c squared. Or do you recognize this triangle? It's just 5. Isn't that pretty? So it's a nice triangle where all the numbers are whole numbers. And so what's y? Well, y is sine. Now that we've figured out that other side, we know that sine, it's going to be negative because it's in quadrant 3, is negative 5 over 13. So y equals negative 5 over 13. Off-topic time number 2. With right-angled triangles, have you seen that one before? Yes. That's a nice triple a squared plus b squared equals c squared, where they all work out nice. Now, (5, 12, 13) is the one that just came up in the question, which is what got me off topic. I saw a beautiful triangle. I had to talk about other beautiful triangles. So here we have 3, 4, 5. Here we have 5, 12, 13. Another one is 7, 24, 25. Your job is to tell me the next one in the pattern. Okay? So before we, if you've seen this before, if you know what it is, before we say anything out, I want you to just tell me patterns that you see. Or if you think you know one pattern that I'm doing, what do you think one of the sides is going to be? So what are some patterns that you see? You think this side's going to be 9 because I'm going up by 2. That is correct. Yes, I'm going up by 2. So the next one's 9, and we can do 11, and then 13, and so on. Okay, so there's the next 3 as far as one side goes. Other patterns that you notice. So you're saying that you think this one's going to be 40 because you're going up 8, up 12, so going up 4 each time. Okay? It is 40. And what do you think the other side's going to be? 41. How come you think it's 41? Because this side is always one more. Okay? That one works. If you do a squared plus b squared equals c squared, that works. Now, I'm going to say we have to skip 11. You're not allowed to ever think about the numbers with 11 whatsoever. Can you find 13? So what I'm trying to get you to do is to use another pattern, because this pattern that was up by 8, up by 12, up by 16, then up by 20, and up by 24, it will work. But the problem with that technique is it's not very good at quickly going, say, to this one when we get to that one. Whew, yeah. Right? How do I know with this one that it's going to be 312 and 313? I'm guessing. You can try a squared plus b squared equals c squared to see if I'm right. But how did I get that? What other pattern is there? Which is what, see, it's these patterns in math. They get me off topic because they're so cool and they're so neat.
If opposite square is 300, so
Yeah. Ramsey thinks he sees something. 64, 65 for right here. Close. Not quite. They're one apart, but. So I'm going to give you something to think about. Red pen, green pen. Oh, they're not going to circle if you hold both of them up. Okay, we'll keep this one green. I'm going to circle these numbers in green. I'm going to circle these numbers in red. That's your hint. If you add them together, 24 and 25, 49 and 7. 13, 5, 20. Isn't that cool? So if you knew 13 times 13 is 169, that will make this 84 and 85. What happens when you add 312 and 313? You get 625, which is 25 squared. But this is a pattern, and it works all the way through for this set of Pythagorean triplets. There are other sets out there, and we run into a bunch of them in this course, and I don't know, every time I run into a Pythagorean triplet, I just think, oh, isn't that nice? So these are ones. The first one that doesn't work with this, there's like the 8, 15, 17 one. But you can explore other Pythagorean triplets on your own time. We should do some more actual math before I get in trouble for taking up too much of your time. Okay. Another thing that we're going to be trying to figure out is where an angle ends. So for example, you have 4,300 degrees. What quadrant is that in? It's a big number. It's a lot of spinning around. So one strategy, and this is a calculator strategy, would be to take 4,300 and divide it by 360. This tells us 11.94 that it's going to go 11 full times around and then another 0.94. If you imagine that, 1, 2, oh man, I've already lost count. So let's say, am I close? 11.94. Oh, one more. Wow! Perfect. Yeah. 11.94. So 11 full times around, and then in the last time around, you go 0.94. So does it make sense that this is halfway around? This would be a quarter of the way around. This is 3/4 of the way around. And so the fact that we're in between 0.75 and 1 should end in the fourth quadrant. That's what I would do if I had my calculator. If I didn't have my calculator, I would just keep subtracting 360s and getting coterminal angles until I got to something between 0 and 360. So in this case, if you subtract 360 11 times, I'd probably start by subtracting 360 10 times, because that would be just 3,600. That'd be easy to do. And then I'd realize my number was still too big, so I'd subtract another 360 and see where it ended up. And I get 340 degrees, so from that, I could figure out that it's going to be in quadrant 4. So that's in degrees. Now, if we think in radians, in particular, most of the angles that we get in radians are going to have pi in them. Remember that that pi still means 3.14. The pi itself isn't a symbol for radians. And that there's pi radians is equal to 180 degrees. But if you get an angle like negative 23 pi over 6, and you're trying to figure out what quadrant it's in, this is the technique that I like to use for that. First of all, I think of that fraction, negative 23 over 6, as a mixed fraction. Are you okay with 23 over 6 being 3 and 5/6? Now, so technically what I'm doing here is I'm taking the fraction out in front and keeping pi afterwards. And it's important to think of it this way because this doesn't mean 3 full times around. How much is it a full time around? Is 2 pi. This is 3 pi's around. Okay? So if this is 0, this would be pi. Here, once around is 2 pi. Once around in a bit is 3 pi here, then 4 pi, and so on. 5 pi, and so on. Can you see that the odd ones happen on the right and the even ones on the left? So when I have 3 and 5/6, and it's negative, so we're going to be going in the negative direction. This would be 1 pi, negative 2 pi. Negative 3 pi gets you to here. And then the fraction, 5 over 6, is bigger than a half. So it will end right there. The beautiful thing about radians is if I ask you what is the first positive angle that's coterminal with, you can say right away it's going to be pi over 6. Because this is a pi over 6, it's going to be coterminal with another pi over 6. So radians are really easy to tell what family they belong to. Whereas degrees are not so easy when they get bigger because you can't just look at it and see which family it belongs to. So this is what we're going to do for radians, especially if there's a pi involved. I mean, if you have your calculator, you could take this number and divide it by 2 pi and do the same strategy as the degrees, and it will work. Okay, this is where we are going to stop today. I've got a worksheet for you.